Hello, welcome to another episode of Xan Talk Show. So today we are going to cover Wolfram language. This is a tutorial from the ground up on Wolfram language or Mathematica. This is a continuation from yesterday's live stream. So video check, audio check. So good morning, talent, Kekma. Okay, so Wolfram language from the ground up for programmers. So it would be great if you have some experience with programming, with Python, PHP, JavaScript, Golang, or any other. So if you have some experience for programming, this is for you. This is, but you never used Wolfram language before, and you never used Mathematica before. So this is for you. I'm not going to cover not calculus, derivative equations, differential equations, linear algebra, number theory. Those are things used by scientists often, mathematicians, scientists, engineers who use Wolfram language, Mathematica, the most often. That's those things, but that's not what I'm going to teach you. I'm going to teach you the programming aspect. Okay, so if you are a programmer, especially you industrial programmers working with, web dev or drivers, Linux, that this is for you, because Wolfram language is very different from all the industrial languages. Wolfram language is a term rewriting system. Okay, so this is continuation from yesterday. Good morning. So let me first of all repeat. You can go to let me show you. Okay, so Xali WolframLang. Okay, so just Xali WolframLang, search it, you will find it. My tutorial I've done. Okay, so go to the top, Wolfram language. I've done so many videos in the past. You can see on graphics. This graphics in particular, I'm very proud of. This is a geometry visualization of a decorative pattern. So anyway, Wolfram language, I've done many videos, over 10 before, but today is ground up. Okay, so so first of all, download. Okay, so you go here and you download it from the Wolfram developer. Okay, and let me explain again what's the difference: Wolfram engine, Wolfram script, and Mathematica. So Wolfram engine, you download it free. It's a compiler. It's basically the compiler, and Wolfram script is the command line interface. So let me demo something different from yesterday. Okay. This is going to be about an hour, 50 minutes or something. So input one, so let's do something. Okay, so let's say nest. We want a nest function f applied to x 3 times. Okay, so that's recursion. Okay, you don't have this feature in all the even functional languages. I don't think you even have it in Haskell or Lisp. So this is how you can do recursion, using a function to do recursion instead of the function calling itself. You simply call the nest function. And you can also do, for example, nest list, which shows you all the history. It creates a list of the nesting. So no nesting x, then first nesting fx, then ffx, then ffx. So nest list, very useful. So let me show you something very interesting. So you are looking at the Wolfram script, which is the interface to the Wolfram language. So Wolfram script, whenever you evaluate something, it sends an expression to the Wolfram engine. So when you download the Wolfram engine free, it comes with Wolfram script. Okay, so Wolfram script is a command line interface. So let me show you something interesting. So let's define f to be a function. Okay, so let me type the whole thing. So actually, let me type in Emacs. So because I have Wolfram Wolfram mod, which allows me to type things much simpler, much easier. So let's define a function. Let's magnify. Okay, function to be, okay, completion x. We want the function to be 1 over square root of x squared plus 1. Okay, that's an expression. So copy that and go back to the Wolfram script, paste it here. So we define the function. You see it formatted in an ASCII way. So now let's do the nest again 3 times. So you see you get this kind of like continued fraction, you know. And now, so this is a demo of the Wolfram script command line interface. Okay, now let's do now let's go to the Wolfram desktop. I recommend you buy it. So now I'm going to show you the notebook interface, which is a graphical interface. Okay, we are going to do exactly the same thing. But first of all, let me copy this here so that we can. Okay, so delete that. So this is today's talk show. This I'm in Emacs, and let's create a WolframLang code. And so here is our code. We delete output, delete the output. Okay, so what is this? Yeah, delete output and delete all this input. So now let's show you in the front end. Okay, so nesting a function, nest list, and now let's do it again. Just show the nesting nest. Okay, a function nested recursion 3 times. And now let's define the function. Function equals to 1 over square root of x squared plus 1. Okay, we define the function. Now let's do the nest again. So you see, so this is the, you can compare, this is the graphical user interface. You got this nice typesetting, and compared to this Wolfram script command line interface. Now when you download Wolfram free, okay, let's go to download Wolfram free. When you download Wolfram free, you get the Wolfram engine, which is a compiler required for, you know, either the notebook or the Wolfram script. You also get Wolfram script free, which you can use here, but you don't have the notebook. Okay, you don't have this. You know, if you want this graphical user interface, the Wolfram notebook, you have to either buy it or buy a Raspberry Pi. It comes with it. Wolfram Mathematica come with it free. So that's about the Wolfram engine, which is a compiler. Then the front end, the notebook, which is a graphical user interface, and you can also do graphics. Fantastic. Okay, so such as we have shown before, you know, you can rotate it and so on interactively. So front end and Wolfram script. Okay, so now let's exit Wolfram script. Let me again show you my Wolfram Wolfram mod. Okay, so we can evaluate this in here. So let's see, you know, evaluate it. Okay, so here is the output. You can see, let's see, you can see we define the function there. Let's magnify, and then here's the here is the output of wait, what? Yeah, so you see, so you are looking at Wolfram mod. Okay, so here's the output. It doesn't do this ASCII typesetting. It doesn't do typesetting. It rather it returns the expression like, you know, pure ASCII. So this is Wolfram mod. Okay, so let me show you. Okay, you can see the source code. So this is you know, the Emacs list source code for Wolfram mod, and it's about 2,500 lines, and mostly it's the Wolfram functions. You know, let me show you. So lots of code, but a lot of it is the you know, all these are Wolfram language functions. There are by default 7,000 of them. So you can see, and you can get this for free. Here is on GitHub. So let's open my website for Wolfram mod, and you can download it on GitHub. Okay, so show JavaScript, turn on JavaScript. So okay, so that's Wolfram mod that allows you to code Wolfram language in Emacs, which is very convenient. So, and I'm using software keys, which is, and the pink window shows all the command calls I do and the keystroke I use. Okay, so that's the Wolfram engine, the Wolfram script, the Wolfram notebook. Let's get you started. You can start to play with Wolfram language. Now, let's continue on the tutorial, the actual start to teach you about Wolfram language. So everything I talked today is already, I have a tutorial, I already written up. So if you prefer reading it, you can just follow through, my website, string. Okay, so let's begin on Wolfram language. Okay, any comments and questions, you post it here, okay? Couldn't run Raspberry in a virtual machine. If you download the Raspberry version, I believe you are limited. You can only run Wolfram language on the machine, on the Raspberry machine. You cannot, kind of cheat, buy a Raspberry Pi, have the Wolfram language free, but then you run it on your PC which is much more powerful CPU. I don't think you can do that. So anyway, I recommend just buy it because, I've been working with Wolfram language since 1993, yes. And then I got to work at Wolfram research in 1995 for half a year. Anyway, so let's begin. Okay, so we have demonstrated the Wolfram language. So first of all, continue from yesterday. Everything, when you want a string is created by double straight quote, okay? Nothing else. Not like Python or, you cannot use single quote, you cannot use triple quote or whatever. Just single double quote, okay? And if you want to escape, if you want to create a double quote, you say \quote. Okay, so that's string. And yesterday we covered in Wolfram language, everything is a function. Okay, now let me show you. Everything is a function. So everything you ever wanted to do to operate on string is all function. So let's show again string length. Okay, for example, here it gives you the length of string, how many characters in it. Okay, so now look at this form, okay? Everything you ever wanted to do, anything, the entire Wolfram language is always just a function call, okay? There's no class concept, there's no object concept, there's no reference concept, there is no special, no object, no abstract class, no static, no member of a class, no constant concept, nothing. Okay, everything in Wolfram language is just expression, and the way you do computation with expression is you call a function like this. So everything, now this is important, this is a fundamental principle of Wolfram language. Everything you want to do is just f function name something argument, okay? And if you have two arguments separated by comma, okay, anything and everything, okay, this is all. So this is the main topic today, list and expressions in Wolfram language, okay? So for example, you can see tutorial expression, list and expression, okay? So all this section, list, creating a list, positioning a list, like the index of an array, in other languages you call it array, index, position of a list, get elements, how do you get an element, extract, sublist and things like that. How do you add element, append, prepend, insert? In JavaScript, for example, you have splice, you have various different names. In Python, you have, anyway. So list, how do you delete an element? How do you change element? So everything, this is what I'm trying to say. Everything in Wolfram language is always have the syntax f something and arguments, okay? So doesn't matter if you want to work on string or if you want to work on something, it's always just a function. It's always have this form, okay? Okay, so that's one thing. So this is a systematic, a systematic grammar, a systematic syntax. So there's no special, there's no. You have to create a class, then you can create an object out of that class. Then when you define a class, then you can have inheritance. When you have a class, then you have to define members, private or something, or you can define a method, which is you can only call a method from the class. But first of all, you have to create an object, then you can have call the method. But you can also have static method, which is like a function. So very complex, OOP, which is a case in Java, Python, JavaScript, at least, and also Ruby. So and also PHP, in all these languages, you have these kind of very complex ideas. They have relations to each other. But in Wolfram language, there's nothing like that. Okay, everything is an expression. 3 is an expression. Okay, a string is an expression. Okay, those are called atomic expressions because they are like you cannot take them apart. Then you build other expressions by having a function like a list. Okay, so Wolfram language is basically mainly derived from Lisp programming language and APL. Okay, I'm not gonna explain APL, but basically like Lisp. Okay, so everything is a list like this, but it uses a different syntax from the Lisp's parentheses. Okay, so everything is just a list like that. Okay, it's called expression. It's actually called, so everything is a list. That's there's no class and references or whatever. Okay, that's one thing. So the one of the advantage of this is that all the functions names are fully spelled out. So for example, you can call this function names and give a string, a wildcard, and type string, and that will return all functions in Wolfram language whose name contains the word string. And this is important because everything you want to do with string is by calling a function, and that function will contain the word string. So all you have to do is find which one function you need, including regular expression, pattern matching for strings. Find the function you need. So this applies to the whole language. So in other things like so this is the advantage allows you to find all the functions easily. You don't have to worry about what's special. The semantics of the language is very simple. Just everything's an expression, and you call function on it to change to get a new value. That's how you do computation. Okay, so let me get on. So let's get on fast. Okay, so it's already 20 minutes. So okay, so function names, everything is an expression. Then you have you call function to do things. Then let me tell you about shortcut syntax. Okay, why? Because when you have everything in the form, if everything is just a function name like that, sometimes it's cumbersome to write it. For example, in Lisp. So let's go to Wolfram language mod, okay? For example, my source code for Wolfram language mod. So you can see, let's go up, so you see you have lots of this nesting. That's Lisp, So in the same way, in exactly the same way, in the Wolfram language, you're gonna start to have lots of nesting. Nesting is not necessarily good because it's hard to read. So Wolfram language has the concept of shortcut syntax. Okay, so let me show you. Shortcut syntax. Shortcut syntax. So let me show you where. Okay, so this is a principle of Wolfram language. Okay. So symbols, not here, syntax, okay? So I did a video dedicated to that topic. You can, in particular, in comparison to Lisp, okay? So for example, you can see this expression, let's magnify, okay? Let's magnify. So you can see this expression. Now, one thing to note is that everything is just nested, okay? So in fact, we can evaluate this, okay? So let's copy it. Let's go here. Let's paste it there. You know, all you see is the function name, for example, the function name here, then followed by its argument. So this compound expression takes two arguments. This is the first one, set something. This is the second one. Then the first argument is again f something bracket. Then it takes several arguments. So the first one is some C array. So this is another argument, coordinate bounds array. Then this function takes two arguments. One is a list, nested list, and the other one is into. Okay, so you can. The point here is that see the nesting. Okay, you are seeing the nesting. So let's evaluate this. So that code returns this thing. Okay. Now there's a shortcut. So the code we just evaluated is exactly syntactically equivalent to this. Okay. So you can see in this form it's much more easier to read. Okay. So let's evaluate it. It returns exactly the same thing. So you can. So you are wondering. So what's going on? So remember, so let me explain this quickly. So remember everything is in this form, okay? However, we defined f. We want to clear f because we defined f before. So now we clear f, fabc. So everything is in this form, right? But however, because then your source code is going to be lots of this nesting, hard to read. So many of the commonly used functions has a shortcut. For example, plus 3, 4. Okay, that's the full syntax called full form. However, for this function plus, there's a shortcut syntax. So you can do 3 plus 4. Okay, same thing with list. Okay, so list z y, okay, that's a list of 2 items. That's the full form. But there's a shortcut for list, so you can write it this way. Okay, that's another example. Same thing with multiplication. Okay, so for example, times, that's multiplication, 3, 4. Okay, 12. Another way to write it is just 3 star 4. Okay, in fact, if between, you can use a space. You can you can just type a space 4. It automatically adds this grayed out cross, stand for it's trying to tell you there's an implicit multiplication. Okay, so anyway, so the point to remember here is that every expression is function followed by something. However, for some of the functions, some of the commonly used functions such as plus, list, times, and many others, there are about maybe 100 of them, 50 of them. There's a shortcut syntax corresponding to the full form. So that's why you see here, this. Let me delete this output. So that's why this part is exactly equivalent to that part. Now, another important thing to know is that when you evaluate Wolfram language, whenever you use the shortcut form, for example, here is a nested list, the first thing the compiler will do is actually transform this shortcut into the full form. So you are looking at this nested list, negative 1, 1, negative 1, 1. The full form is here, okay? You see? So that's what the compiler do. So it will, whatever shortcut you typed, it will first of all translate internally, transform it to the full form. Then it does computation. So in other words, unlike many other languages, you have so-called sugar syntax, okay? Meaning that you can type this way, it kind of equivalent to another way. But in the Wolfram language case, they are exactly equivalent, 100%. So this is not just a short syntax sugar. It's 100% equivalent, because the Wolfram language transformed this shortcut into the full form first. So in other words, when you program Wolfram language, you want to think of this way. So you want to think of everything as the full form, because that is the real thing Wolfram computes. The shortcut syntax is just for visual, easier understanding and things like that. What actually matters is the full form. This is important because when you start to get into advanced programming, like pattern matching, it's always done with a full form. Okay, it's like when you want to match a pattern, like 3 times something. And things can be symbolic. Okay, so for example, let me show you. Times xy. It just returns xy. That's symbolic. You cannot do this with most languages. Most other languages, it will tell you, oh, x is not defined, y is not defined. You cannot multiply them. But in Wolfram language, because it's symbolic, you can. Now, Lisp is also symbolic, but however, Lisp doesn't go all the way. So if in Lisp you say x times y, it'll give you an error saying that x is not defined. So that's some technical detail. Let me show you, okay? So XOR Emac Lisp mod. So for example, let's magnify. So times 3, 4. So evaluate, okay? So evaluate it. So you can see the output is here, 12, right? But if you say evaluate x, y, you'll see error. You see debugger entered error void variable x. Okay, so but what if you quote it? So for example, let's try this. This way. You still get error. You see, wrong type of argument, number or marker p. So even in the even Lisp is also symbolic, but it doesn't go all the way. So Wolfram language can. So let me talk about pattern matching a little bit. Let me show you the power. What's the deal? What is the advantage of this, symbol thing? So for example, let me show you a pattern matching. For example, we have done, let's start Wolfram script, okay? And we have done, let's copy that. Let's put that to, okay, so let me go, hold on a second, okay? Let me get to let me log to what we talked about. Okay, so let me log what we talked about. So today's talk show, we talked about some of that, and now I want to demonstrate symbolic pattern matching, the power of pattern matching. Okay, so so okay, hold on a second. Close that. Wolfram mod. Okay, I want to show you Wolfram mod. Close that. Paste it here. XOR Wolfram mod, so you can have a link to it. Okay, so let me demonstrate symbolic pattern matching. Okay, so first of all, let's copy that, okay, and paste it here. Paste anyway, yeah. So evaluate. So you get the list. Okay, so let's do it. Let's do list. Okay, so you get the expression nested f. Yeah, there's a bug. I think there's a bug when you try to copy paste it. Things get screwed up. So exit, you type exit to exit. Let's start again. So copy that. Okay, magnify, and we want we want to nest it, okay? Paste it, okay? We define the function. It's still screwed up. Okay, we let's start a new new terminal. Now I wonder if it's because the bug came from. I wonder if the bug came from the Windows terminal or PowerShell terminal. Right now, okay, so let's switch to using the PowerShell terminal because the PowerShell console, because I was using the. Okay, so let's not get distracted. Okay. Okay, if you are using the PowerShell, the Windows Command exe, it doesn't even you cannot even post. Yeah. Okay, let's get back to using the Microsoft Windows terminal. Okay, let's start it, copy it, paste it. Okay, now it's correct. Now let's nest this function. Yeah, I don't want that. Paste anyway. What? I don't want paste lines, okay? There it is. I think what happens is that if you paste something that contains line return, it'll screw up things. Okay, so now you see we got the expression. Now let's evaluate this in XOR Emacs mod. I mean XOR Wolfram mod. Okay, so let's do it again. Okay, so evaluate it. I need to got too much. Well, it won't let me unless I exit here. So yeah, it's kind of painful. I don't want to exit there because it only allows like one process if you are using the terminal, something like that. So I can probably fix it because I have a the proper Wolfram desktop. Anyway, so what I want to show is that so anyway, so what I want to show is that the power of symbolic pattern matching. Okay, so right now you see this expression square root 2. Let's see, nested 3 times. Let's say nested 4 times. Copy it. Let's do it over here. Okay. Copy it. Wait, so there is only one square root. I want what I want is multiple square roots. Okay, so we can fix this. So let's redefine our function to be plus 2, okay? Let's redefine our function to be that. Then let's compute that. There it is. Now we got multiple nested square roots, okay? Now suppose you want to you can look at, so this is typesetted format, okay? Now you can look at this in full form, okay? So let's so you can see the actual expression. You see, this is the fully nested syntax. So you got power plus something plus 2 plus power. You see power over -1. That's the inversion, 1 over something. The full form is, let me show you, okay? So 1 over x, this is a normal form. But if you do full form, 1 over x, it's 1 over 2. Oh, that's a rational. Wait, I want to do actually 1 over x. You see, so that's power x raised to negative 1th power. That's math, okay? That they are equivalent. So you got this expression, you got this nested square root expression, and the full form is this thing. And now let's say you want to replace all the square root by, let's say, square to the 3rd power. Okay, so what we can do is that, let me show you. Replace all takes 2 arguments. The first one is the expression, whatever you want to replace, you do replacement on. The second one is a rule. Let me use the full form so it's easier to understand. So a rule, you want to replace all square root by you want to replace all square root of anything inside, let's name it x. You want to replace it by, let's just say y, okay? Let's do it. Oh God, it's replaced. No, this is not correct. Let's say this, okay? Okay, so wait. So what I want to show is you want to replace all square root by, let's say, some function f3. Okay, so what? This is, we still have square roots. Why is that? We want to replace all square root by, yeah, what's going on? Okay, am I still, is it interesting? Any questions? Good morning. Wolfram, you won't work because you are trying to multiply 2 symbols. Yes, exactly. That's what I'm saying. But in Wolfram language, you can do that without, it just come out symbols. Then, okay, anyway, so okay, so let me demonstrate this, okay? This is easy to demonstrate. Times x, y, okay? So you see, now if you say x equals to 4, okay, then you re-evaluate time x, y. So now it becomes 4y. And if you say y equals to 3, and then you re-evaluate this, you got 12. You see, that's the symbols. You see, if a symbol doesn't have a value, it's gonna compute anyway. It's just gonna return the symbolic result. So this part is more advanced than Lisp. Lisp doesn't do that. You have to, your symbols has to become a value. Otherwise, it refuses to return it. So anyway, so this is a good illustration actually about the term rewriting system. So in Wolfram language, everything is symbolic. It's just an expression. Like you can almost think of them as a string. It just transform the string. That's all it. The terms. Okay, so let me go back to this. I want to demonstrate this, but it failed. So I want to replace, so you see we got this thing, which is full form, which is this. I want to replace this expression by, let me do it the normal way, okay? The normal way I'm familiar with. So square root, replace it by, first of all, we need to clear x and y because we defined them before. So clear x, y, then I want to, and by the way, here's another advantage of the notebook interface, because in notebook interface, you can place expressions anywhere. Like you can go edit here and reevaluate this part. You can go, and you can see the history of the whole thing. you know, but not in the command line interface, which is the case for Python, for Ruby, you know, for JavaScript, Deno. You know, you have to, you know, each time you only see one part and you cannot edit arbitrarily, you know. So this is the advantage of a notebook interface. So, but anyway, let's go back to here. I want to show you how do you do this. Okay, so I want to replace square root, the symbol square root, by F3. Oh yeah, that doesn't. Oh, that's why it doesn't work. I know now. I know. You see what you see. This is actually tricky. This is more advanced. You know. So I want to replace all square root by F3. So I'm expecting a result where all this square root is just a function called F3. F3 will do whatever. But it failed, you know. So why does it fail? Because actually the square root does not happen anywhere, you see. But instead you have the power -1. So power -1 is like the inversion, 1 over something. But you have the rational. So what rational stand for? So for example, this rational 1, 2 is 1 over 2. So the square root actually doesn't happen anywhere in output. So this is important. That's why I mentioned before, when you do computation, especially when you get advanced into pattern matching, you have to know what is the actual full form, not the shortcut expression, you know, not the shortcut like 1 plus 2, where is it? You know, all these are shortcut. For example, x equals to 4, the full form is actually, let me show you. So full form, you code hold, so it doesn't evaluate. Then you give the expression x equals to 4. It's gonna be set square bracket something, you see. So you see, the full syntax, the full form may not be what it seems. So this x equals to 4 is very convenient, very intuitive, you know, x equals to 4. But actually, you have to know when you get advanced. This is important, you know. So when you start to learn Wolfram language, try to understand this. The syntax shortcut is just the visual syntax shortcut. The real computation is always done with the full form. So almost by heart, you know, once you code Wolfram language for a year, you will or you should know all the syntax shortcuts, what they actually are. So let me show you, where is it. So Wolfram language tutorial, go to my tutorial, Wolfram language basics, then you go down to the syntax. So, you know, there's a full video on that. So you can see here is a list of essentially all possible syntax shortcuts used in Wolfram language and how they correspond to full form. For example, let me show you an example. So for example, this one, question mark A. So what does that mean? So when you type question mark, let's say full form, you know, you want to know what this function does. That's how you do it. It spit out a helpful information. Then you can click on that. Then it tells you the full detail and examples, how to use it, what does this function do. Everything is function in Wolfram language. So, but however, you see that question mark something, that is not the format of F something. So actually there's a full form for that, and that is the information. So the proper way to do this is actually like this. Information, okay, so complete, then a string, full form. You see, that's not equivalent actually. Anyway, the point is that, you know, everything is in this, you know, fully function form with square brackets. Okay, so let me get back to, so so that's why here we failed, but we can get it to work. So instead of a square root, let's replace, let's go here, okay? So we want to replace all the square root to something else. So we say, let's see, rational, power, power -2. Okay, so now I get it. So square root, so here is the way to see why it is wrong, why it's not working. So you can say full form square root of x plus 1, okay? Actually, you have to, let's say hold. It's always good to say hold, but otherwise you'll just evaluate it, okay? That still doesn't work. Okay, this is not a good example because it's getting too tricky. I mean, the tricky part is that how does the square root, you see, basically what happens is that square root becomes, part of it becomes rational something and part of it becomes power something. The reason for that is, anyway, let me quickly just get it to work, okay? Let me quickly get this to work. So let me, because I know how it does. So I want to replace everything power, P-O-W-E-R, power, two parts, x numerator and y the denominator, okay? I want to replace it by function f3, whatever that is, and replace it by xy, okay? Do it. Fantastic. Wait, what? Yeah, it doesn't work. Well, it doesn't work because you have to say replace repeated. Okay, let's try again. Yeah, now it works. Okay, so okay, so that's getting a little bit complex. The reason you see it does not work before it, because it only replace one instance. Okay, so let me explain, since we are on this. Let me explain, okay? So replace, okay, let me explain the whole thing again. So we are doing replace the expression by a rule, and this rule is power. Okay, whenever you see power, replace rule takes two arguments, okay? The first part is what is the pattern, okay? I mean, the rule takes two arguments. So replace takes two arguments. The first part is the expression, the second part is a list of rules, okay? Or just a single rule. So right now we are using a single rule, and the rule has two arguments. One, the first part is the left-hand side. What do you want to replace, what pattern you want to match. The second part is the actual, the thing you want to, what you want to become, okay? So the pattern, right now we want to say a pattern. The pattern is power something, power two things, okay? And one thing inside is x underscore, okay? The other thing is y underscore. Underscore means anything. So you want to match anything that's power anything, two things inside, and you name it x and y. You name it so that you can put it in the replace part. So for example, in the replacement we can say g, okay? So g x y, okay? Now if we evaluate that, you see you still get square root here, which is a power something -1. The reason is that this replace function only does it one time. So you'll find the pattern, you'll replace it, and return the result. So if we want to replace all the square roots, we have to say replace repeated, okay? So this is advanced detail of pattern matching. So let's do it again. So you can just call replace repeated. Okay, there it is. Now you can see why it works. So we got into some rather advanced part of pattern matching, which is not planned. Today I was just planning to go over lists, but I was trying to show you some power of pattern matching unplanned, and got screwed up and got more and more into detail. And so pattern matching, you can find my tutorial on here. First of all, introduction, and then pattern syntax. So since we're talking about this, let me tell you what pattern matching is about. So again, remember, in Wolfram language, everything is symbols, symbolic, okay? It can be numerical, but it can be symbolic. So if you have numbers, it returns numerical results. If you have symbols, so whatever symbols, it returns symbolic result. Once you have a value, it give you numerical result, whatever. So symbols, everything is symbols. All expressions are symbolic, okay? Then symbols, okay? So then because Wolfram language is a term rewriting system. So what does that mean? Basically, the way it computes is that it replaces a sequence of symbols by some other, which we have seen, like this example, we replaced all the square root by F3. So this is, so here, it's easier to see here. By the way, if you are wondering what are these slash dot and what is arrow, those are just syntactical shortcuts. So slash dot is a syntactic shortcut for replace repeated, okay, here. And that arrow symbol is a shortcut for the rule. Okay, so but if we use this full syntax, it's easier to understand. This is not full syntax yet because we have the underscore. The full syntax for underscore is blank something, but it gets tedious, so I'm not going to go over that. But anyway, my point here is that we demonstrated symbolic pattern matching replacement, which is a term rewriting system. Everything is a symbols. We can just replace it, part of it, by a pattern. Okay, including deeply nested parts. For example, if you are gonna do this in Python, in JavaScript, in Golang, you cannot. Okay, I mean, first of all, they don't deal with symbols, so you can't have this. You cannot have this G something, because it'll just say G is undefined, X is undefined. Okay. But even if you give them a number, so suppose we replace all G by, we can do that again. For example, let's say G becomes 3. Okay, so let me just use the shortcut syntax. Okay, so now it's all symbols or numbers. Okay, but anyway. So even in Python, even if the whole thing is just numbers, you still cannot do this replacement because you can see deeply nested patterns. When you have in Python, in JavaScript, in Golang, in PHP, when you have a complicated nested array or list, you want to replace some part of it. You can't just do a pattern replacement because they don't support pattern matching usually. I mean, even in Haskell, I think I'm pretty sure in Haskell, because in Haskell, in OCaml, they have pattern matching, but they do not allow you to do complicated nested pattern matching. So, but in Wolfram language, you can nest it, the patterns in fairly complex ways. So one way to think of this term rewriting system is to compare it to string replacement of regular expression. So imagine if you have a language that all it does is do string replacement with regular expression. You call some regular expression, using a regular expression pattern and just repeat. And then, so that's kind of like what Wolfram language is doing, except you are not dealing with strings. Strings are just flat usually, so you don't get to nest. So string is hard to work with because you have to everything becomes, you cannot take them apart. But so the analogous of string is symbols, sequence of symbols, and you replace them by the pattern becomes symbolic pattern syntax, analogous to regular expression. Okay, I think that's it for today. So so we talked about for an hour, and that's it for today. So we went to some pattern matching, and that's it for today. So we're gonna shut down in 2 minutes. Any more questions? So we covered expression quite a bit, and but I didn't show you every all the other things about list and expressions, many other functions. So at the end, let's show you something interesting. Okay. Let's use the table example. So we are going to create massively nested table. Okay, for example, let's one. Let's see that one. Okay. Yeah. Okay. Let me explain table. Okay. So first of all, let's not do this massive. Okay. So table is a function that takes two arguments. The first argument is an expression. The second argument is a kind of an iteration spec. Okay, so table lets you generate a list or nested list, arbitrarily nested list, or you can think of it as generate a matrix of any dimension or tensor. Okay, so it is analogous to Python's list comprehension. So let me show you an example. So let's say X, okay, so it generate the list. Okay, so let's say X125. Okay, very simple. And you can say X plus Y 125. Okay, and let's say X squared plus Y generate 125. Now let's say 125, but in steps of 1/2. Okay, you see. Now remember, you see these fractions. These are simplified rationals, so it will automatically simplify. For example, if you have 9/3, it simply becomes 3. But if you have 9/4, it's 9/4. So if you have large number, let's say 2, divided by over let's another random number. Okay, it simplifies for you the fraction, and it doesn't become a float. In most languages, most of the time you just get a float. But Wolfram language, remember, it's symbolic, so that's why it maintains the form. So in here we did several table examples. Let's the function can be arbitrarily complicated. For example, times, let's say times our function fx. Remember we defined f before, so now it becomes that. Okay, now you can have multi-dimensional. Now let's say y goes from 1 to 2. Now you are getting a matrix. Okay, so this is becoming very complex. Let's simplify. Okay, so let's simplify. Let's not get too complex. Let's just say x squared plus y squared, and x goes from 1 to 3, y goes from 1 to 2. So this is easier to understand. Wait, they got a value. We don't want the value. Clear x and y. Okay, and run that. Oh yeah, they yeah, they become a value because obviously we say 1 plus we say because they evaluate, because x is a number raised to the second power, it becomes a number. But let's give it a symbol. Okay, n and m. Okay, so that's the that's a matrix. Okay, so yeah, okay, so or we can do it this way. What am I trying to show? Let's just say x plus y. No, let's not. Let's just say at least xy. Okay, so this way it gives you, yeah, that's what it's supposed to be. Yeah, so for each x you go you iterate x equals to 1, x equals to 3, x equals to 2 to 3. Then for each y you repeat. So you can show the result. Let's say xx equals to the that. Okay, you can say matrix form. Okay, so it shows you the matrix form. You can also say tree form. Okay, so it shows you a tree form. So that's what's interesting about this. So now let's do a tree form of this complex thing. this complex tree. So that's that's a power. Wait, can I magnify? Okay, so that's it. Thank you guys for watching. If you like my stuff, donate. Okay, go to my Patreon, my PayPal stuff. Bye, guys. Shutting down in a minute. Bye.